Okay, so welcome everyone to today's UQM seminar, which is actually the last UQM seminar of this spring's seminar series. At some point, we'll probably get started again over the summer, but I'm not sure of the exact date. So today, it's a pleasure to have Amir Raz from UT Austin, and Amir is going to tell us about subsystem conformal symmetries.
Thank you for having me. As you said, I'm Amir. I'm currently a graduate student at UT Austin, and I'll mostly talk about a paper that came out a few months ago with Andreas about subsystem conformal symmetries and fractons. So before I talk exactly about what we did, I'll go over a little bit about the background and maybe the big picture stuff, which is quantum field theory and how fractons fit into our general ideas of quantum field theory. And so we're all taught kind of this big picture idea where we start with some UV physics. It could be some sort of condensed matter lattice theory. It might be some high energy strings, something particle physics theory. It could also be a statistical spin on a lattice. And then we do some RG flow to look at the IR physics. And we zoom out and zoom out and zoom out. And then we land either on a conformal field theory or a topological theory or maybe some sort of trivial theory. And that's all we can basically end up in. Really no matter what UV physics we started with, we can completely ignore it. And everything is described by this IR physics. And this kind of fits into a broader picture where we can start with any theory, have our conformal theory or topological theory, add some perturbations. It might be topological excitations, maybe some boundary modes or something more exotic. And this is how we can describe all phases of matter. This is kind of the Wilsonian paradigm of quantum field theory, that we can completely ignore any UV physics and how we came about, and just focus on the continuum quantum field theory, which is some topological or conformal field theory plus some relevant perturbations. And this is a very powerful tool for high energy theorists, for condensed matter theorists, for anyone really in the field, and it's very universal. A lot of different theories fall into this very simple paradigm. Unfortunately for us, not everything falls, at least not nicely, into this paradigm. And maybe the recent example of something that doesn't is these things called fractons. These are these new exotic models, and really their main idea, the main properties that they have is that they have particles, which we call fractons, that have restricted mobility. So these particles can really only move on planes or lines or not move at all. So they have fractional mobility. These models also have a subextensive number of ground states. So the entropy will grow linear in the system size. So this is different from a topological field theory where we have a ground state degeneracy, but it's some fixed number, or different from the case where we might be used to, where the entropy grows like the volume. So this is somewhere in between those two. It also has explicit breaking of rotational invariance. So that's another interesting property. And it has these exotic global symmetries that act on planes or lines or some subsystem of the whole system. So like in the X cube model, we have flipping all the spins in a given plane, and that's some global symmetry of the system. So because of all these properties, this doesn't really fit into our nice, neat Wilsonian paradigm. And so what can we do with this? Well, one option is to just go ahead and send the mafia and take down all the hundreds of papers containing fractons in the archive. Probably isn't the best idea, but that's one possible. But really what we can do is one of two things. It's either accept that not everything fits into this paradigm, and so focus on the lattice models and keep up finding new exotic, exactly solvable models, or maybe come up with some hybrid descriptions that fuse quantum field theory and maybe a little bit of lattice structure, something like a foliated quantum field theory, where you have quantum field theory foliated in space. And so that's not quite a quantum field theory, or at least doesn't quite fit into the Wilsonian paradigm. But it's not quite a lattice model, it's somewhere in between. We can also instead try to expand our definition of what a quantum field theory is. And in this case, come up with new continuum quantum field theories and try to understand their properties. So these things that fall under this category would be something like the tensor gauge theories, where you have a symmetric tensor, or other theories where you have an exotic global symmetry, and these are continuum quantum field theories. At least formally, they seem like a continuum quantum field theory, but they don't. But they require us to expand our idea of what fits under the Wilsonian paradigm, and that's really what I'll talk about. I'll talk about how these theories force us to expand what we think about as a quantum field theory and how they fit into a Wilsonian paradigm, or how we can ask if they do or don't, and exactly what that means. So if we want to take these new quantum field theories and fit them into the Wilsonian paradigm, then we really need to modify it in some way. So again, we might start from some UV physics on a lattice, but then we need to somehow modify where we can end up in. So instead of just having our regular options, just conformal field theory or topological field theory, we need to add these fractonic RG fixed points, or maybe fractonic conformal field theories that are also RG fixed points, but have a lot of properties of fractons. And then on top of them, we'd also need to add what relevant perturbations they can have, like particles, excitations that can't move, and these, or can only have some sort of restricted mobility, and kind of come up with a generalized or modified Wilsonian paradigm to incorporate everything we know under the same roof. And so really, if we want to describe these fracton models using quantum field theory, we need to understand these new RG fixed points and what they are, how to find them, what properties they have.
Excuse me.
Yeah.
Your fracton RG fixed point gapless or gapped?
Well, by their nature of RG fixed points, this is going to be a gapless theory, or yeah, right? If you think it might be a description of some second order phase transition, you'd hope them to be gapless. And then you can add, so if you want to discuss gapped fracton phases, then the gapped phases would be on relevant perturbations on top of some fixed point. So if you have an extensive number of ground states, that means your fixed point isn't quite one of these three, but it has to be some sort of RG fixed point, some new RG fixed point. And on top of that, you would add excitations, gapped excitations, right? That would create your gap theory, kind of in the same way as the Wilsonian paradigm. That makes sense?
Yeah, thanks.
Okay. Okay, so these RG fixed points, so what kind of symmetries should they have, or would we want them to have? So first of all, they need to be RG fixed points. So we need to have scale invariance, and we need to have translational invariance. Otherwise, it's just not a continuum quantum field theory. We wouldn't want them to have full rotational symmetry, but definitely having some discrete rotational symmetries is a property that is beneficial, and also having some sort of exotic global symmetries, like the dipole global symmetry, or maybe a tensor gauge symmetry, or some other exotic global symmetry. And then we can start asking, well, if we just look at models that have these properties, that have these symmetries, what properties do they have? Can we maybe classify something about them, their behavior? And what I'll focus about in this talk is, do they have any emergent conformal structure? And this is the question that we were interested in studying, because typically scale invariance plus rotational invariance implies, at least in a broad category of theories, that you have some sort of conformal invariance to your theory. And really, most of the RG fixed points that we know of, they don't only have scale invariance, they have more than that. They have some conformal structure. And so we wanted to know if we can find any conformal structure in these types of theories. And maybe that can help us also answer some of these other questions. And so really we went to start exploring this question of do they have some conformal structure, by looking at some simple examples of quantum field theories of fractonic RG fixed points, and seeing if they have some emergent conformal structure, and if we can describe it in some useful way.
Excuse me, sorry for interrupt again.
Yeah.
Since you say the fractonic RG fixed points regard as some continuous second order, perhaps quantum phase transitions between other neighbor phases, are that those neighbor phases necessarily also fractonic, or do you know also the property around the neighbor phases? Just conceptually.
I mean, I don't see why they necessarily have to all be fractonic. I mean, if you add operators that break completely the global dipole symmetry, they very well might not be fractonic, right?
Okay, thanks. But so this gapless phase fractonic property might be also emergent, just at a critical theory.
It might be. I mean, this is all new stuff, and really the fixed points I'm going to be talking about today are these free field theories. And so if you want to look at interacting, if you want to try and answer questions about interacting RG fixed points, I don't know how much you can say about that yet, right? This is still very much an open question.
Yeah, thanks.
No. Okay. So maybe one of the simplest models to look at is this model that comes from the XY plaquette model, and its continuum description. And so it just involves a single scalar field. Typically it's taken to be compact, but we don't necessarily have to. And it has a normal kinetic term and another term that has these two spatial derivatives. And so now we're working in 2+1 dimensions. Because this is a free theory, it will be a lot easier, free or Gaussian, so it's a lot easier to study. It has a square lattice symmetry of 90-degree rotations, and it has this subsystem dipole symmetry where we can shift phi by any linear function of x and any linear function of y. And so this is a symmetry that acts on lines. And yeah. It's also scale invariant, and it has actually two scale invariances. We can independently shift x and t by rescale x and t, and we can independently rescale y and t. And so we see that we have these two complementary scale invariances of this theory. And so it fits all the requirements of being, at least just by inspection, it seems like it fits all the requirements of being a fractonic RG fixed point. And so we can ask, is there any sort of conformal structure here? Is there any extended conformal invariance that this type of theory might have? And it turns out the answer is yes. This type of theory does have extended conformal structure. And the way to see that is to move to these fixed momentum modes in one of your two directions. So for example, you can Fourier transform in the y direction. And so look at fixed momentum modes in the y direction. And the resulting Lagrangian is just a free relativistic scalar field in the xt coordinates. So this is just a free scalar field. And it does have this ky squared here, which sets the speed of light. But really, it still has the full relativistic two-dimensional conformal symmetry for each ky mode. And so here ky can be thought of as some independent variable. So we have this full subdimensional conformal symmetry because now it only acts on the xt coordinates, where ky is some free parameter, and it contains dx. And we can do the same thing, just transforming in the x direction, right? Chose to transform in the y, but really we can also transform in the x direction. And that gives us another set of conformal generators, this time that contain dy. And so we have these two subdimensional conformal symmetries of this model. Now, one interesting thing about these symmetries is that they don't commute with each other. And this just comes down to the fact that ky, which is just the momentum in the y direction, or py if you want, doesn't commute with y itself. And so if we write down the conformal algebra of these of all these generators, you can just start commuting everything, and you see that the global conformal transformations between these two algebras don't commute with each other, and they generate new additional symmetry operators. So you can just commute them and you get new operators in your algebra, and you actually need to add infinitely many additional terms in order to generate the full algebra, right? You just start with these two conformal subdimensional symmetries, you can start commuting everything, and you just generate a giant algebra that doesn't seem to have any known structure. It does seem to be very large. And so now that we have found that these this conformal structure, even if we don't necessarily understand it, definitely exists in such theories, we can ask if we can come up with any other simple models that also have the same behavior. And maybe some of them will also have nicer conformal structures. And so maybe we can come up with examples where this algebra isn't infinite dimensional, or maybe where we can actually think of what this algebra constrains, or how it constrains the theory.
Can I have a question at this point for this model? So you are discussing some kind of conformal symmetry in this model. Is there something like an operator state correspondence? In ordinary CFT, we have that, but for this model, do you know of any such operator state map?
We didn't look into finding an operator state correspondence for this model or for any of the models that we'll look at. But that is definitely something you can try and do. It might be a little strange because these symmetries don't commute with each other, but
it's not obvious because you went to the momentum space already, right? So
yeah.
Whatever you map to might not be a local operator.
Exactly, and it turns out that a lot of them are not local operators because they have momentum to some negative power.
Right.
And so maybe you won't be able to find it, but I can't give you a definitive answer. It's a good question.
Thanks.
Okay, so so we wanted to find maybe a few other examples where we can come up with simple models that also have this subsystem conformal symmetry, but maybe have some nicer conformal structure. And so we looked at 4 models in our paper that are very similar to the original model. They're given here in Euclidean signature, but you can always do a Wick rotation. So this first one is just the same model that we saw before, maybe with a complex scalar, but again, you can just take it to be a real scalar if you wanted to. And then we looked at models that have, instead of 4 spatial derivatives, 2 spatial derivative term. And instead of a relativistic kinetic term, you can also have a non-relativistic kinetic term. And all these models are free. They all have a global dipole symmetry, yeah?
Yeah, so in the early discussion, in the discussion up to now, and also in the original sort of study of, work going back to Perma-Conti, phi was a Goldstone mode, it was a phase. While here you're now transitioning in using the same symbol, but thinking about it as a, as a field. More importantly, is not that it's the field whose phase is the field appearing in the previous model, in the Perma-Conti company model. So I'm just, it's kind of a change of perspective or change of really the physics in some sense.
So,
one is describing critical theory and the other is a Goldstone mode theory. It may not matter for classification, but it's...
Yeah, so it doesn't really matter when you just look at the, as we were interested in looking at the space-time conformal structure of such Lagrangians. But it's not quite true that this theory is like if you look at the phase of this first theory, it doesn't quite fall under the previous theory, right?
Right.
4 derivative term. You need to do something else to, and this is well known. You need a 4 phi interaction term, 4 phi term, a very specific 4 phi term in order for that phase to become the Goldstone mode.
Right. So the upper left theories superficially looks similar, but it's really distinct theory from what you discussed before, right?
Yeah, it is a distinct theory, but it has the same space-time conformal structure, and that's what we were actually interested in this paper. But it does have definitely a lot of other global and other issues that are very different. Any of the question of winding modes, any question about the spectrum, these are all very different theories, depending what, if you think of phi as a real scalar, as a complex scalar, as a compact phase.
Okay, thank you.
It definitely changes everything. In these non-relativistic theories, you can think of phi as a fermion as well, and that's also fine. It doesn't change the conformal structure that we were interested in, but it definitely changes the spectrum and everything else.
Okay, thank you.
You're welcome. Okay, so I asked if these theories have an energy spectrum that's bounded from below, especially the right columns. That's another good question. So a priori, they don't look like they're bounded from below. This first theory actually is fine. Well, they're both fine. For the non-relativistic theory, you can simply take a fermion and then fill the Fermi C up to half filling, and then everything is fine if you think of phi as a fermion for this theory. And for this theory, it will turn out, and I'll actually show you why it's a perfectly valid theory to think about where phi is a boson. But again, at least on the level of a free theory, we can formally write down these Lagrangians and ask what type of conformal structures arise from them, just as kind of a exercise to try and understand what kind of behaviors we can expect from these types of theories, even if these aren't necessarily good theories to describe models. We can still try and learn, like have them be some sort of simple toy models to learn about the conformal structure of fractonic RG fixed points. So I hope that answered the question in the chat.
I'm sorry, can you explain again why the two theories on the right have a sensible spectrum as far as being bounded from below?
So this bottom theory, it's just a non-relativistic theory. And so we can take phi to be a fermion. And then we don't, and then the whole boundedness from below it isn't an issue, right? We can.
Okay, let's talk about the theory in the upper right.
Okay, well,
I'm simply repeating Michael's question.
Yeah, I know.
If you take a configuration, say time-independent configuration, then I think this object is not positive definite.
That is
dx dy phi integrated over x and y is not positive.
It's true that it doesn't seem to have a good spectrum, but we can study it nonetheless, at least formally, just looking at the conformal structure of the Lagrangian. I actually want to discuss this theory in more detail, so maybe we can wait with this question until a few more slides, if that's okay.
But also just a comment, the lower right, even for bosons, that's a non-relativistic Lagrangian for Hamiltonian that has a bounded spectrum that's bounded from below.
This one?
No, the lower right.
Yeah, okay.
You know, if I have a Hamilton, if I think of the Hamilton corresponding Hamiltonian, then it's just harmonic oscillator with
well, you have a px py here, so
oh,
so,
I see. If you fix one of them.
Yeah.
Oh, okay.
you can have modes where Px is positive and Py is negative, and so.
Okay, yeah, thank you.
Yeah, so it doesn't seem like it's bounded from below. But again, if you take it to be fermions, then everything should be fine. Okay. Thank you for the questions. This is very good. So just maybe a complete, before I talk about this 2-2 model, which Nati and other people wanted me to maybe talk about a little bit more. Just maybe a little recap about these models. They're all free 2+1 dimensional models. They all have some sort of discrete rotational symmetry. The 4 spatial derivative terms have a square lattice rotational symmetry, while the other 2 have a rectangular lattice rotational symmetry. They all have the same dipole global symmetry that we talked about before. It's more obvious in the 4 spatial derivative term, but even the 2 spatial derivative term, the Lagrangian transforms up to a full derivative, and therefore it's still a global symmetry of the action. And they all have a subsystem scale invariance. And it turns out that they also all have a subdimensional conformal symmetry. In the case of these 2 models, it's a non-relativistic conformal symmetry, Schrodinger conformal symmetry. While in the other 2, it's some sense a relativistic one, maybe just holomorphic. And 2 of them actually conspire to create a well-defined extended symmetry, while the other 2, the operators, simply don't close in on themselves. We saw this for the original model that I talked about before, but it also happens in this 1-4 model. And so maybe coming back to the question from before, I'll talk a little bit more about how, for example, the 2-2 model both makes sense, and how the conformal symmetry of this model becomes something that's sensible, not just infinite dimensional, like what happened before. And so if we start out from this model, we can do the same exact, at least formally, we can do the same exact idea of transforming into Fourier modes in the y direction. And we get a theory that looks like this, with some parameter here, but a single derivative in the x direction and 2 derivatives in the time direction. And this looks like a non-relativistic free field theory. Indeed, space and time are reversed here, but it still looks like a non-relativistic free field theory. And so we can write down the non-relativistic or Schrodinger conformal symmetry in 1+1 that this theory has. And so we can just start listing out all the different generators of the symmetry. And so the first ones are translations, of course. The model of translation is invariant. It also has these 2 scalings. You can scale space and time, and we can scale, well, x and time, and we can scale y and t. And in both cases, this field phi has a scaling dimension of 1/2. And then we can write down the special conformal transformations. And this is just implementing the special conformal transformations of the symmetry of a free scalar field in 1+1 dimension, a free non-relativistic field in 1+1 dimensions. And then we also have the Galilean boosts, because this is a non-relativistic field theory. And those are all our conformal symmetries. And so they fall into this subdimensional conformal symmetries where H is shared between the 2 subdimensional conformal algebras, but otherwise py, dy, cy, and ky, all these generators together form the 1+1 subdimensional conformal symmetry in the y direction, and the other 4 plus the Hamiltonian h form the subdimensional conformal symmetries in the x direction. Now for this theory,
Remind us what delta is.
it's the scaling dimension. So if, delta is the scaling dimension, and in this case, delta acts on the field phi by scaling it by -1/2. So phi has a scaling dimension of 1/2.
Okay, and the other question, I don't, can you go back to the previous slide that you showed?
This one?
Yes. So how should we think of these kx and ky? Should we think of them as d by dx and d by dy or not?
So that's exactly this next slide. Yeah, they are just the momentum operators in x and y, and so we can, in this case, we can interchange them completely because everything is just linear in kx and ky, and so we can just write down what they are. In the previous case, we had k8. If you write down the conformal generators, you get something like ky to some negative powers, and so you can't just well, you can formally just interchange them, but that means you have some sort of non-locality. But here, all the generators are local, and we can just work with dx and dy.
And if we commute these gadgets here on this slide, what do they close on? What?
You're taking away my talk.
Sorry, keep going.
Here, why don't I go to the next slide? No, it's fine. This is the natural progression, right? The next thing to ask is, okay, we have all our generators. What do they close on? Do they generate anything new? And we can just commute everything, and we need to add one extra operator, which we call C0, and then everything closes in on itself completely. And you can just commute everything now and see that what all the commutation relations are. And now we have a closed algebra with 10 generators. And we can ask, okay, what is this algebra? Well, you can just by commuting things see that it's a simple Lie algebra with 10 generators. We know exactly what that is. So the full algebra is an SO23 algebra. It's some real form of SO5, and it's actually SO23. Which turns out to be the relativistic conformal algebra in 2+1 dimensions. And somehow,
just to understand the notation, the vertical line between the 2 and 3 is what is often denoted with a comma?
Yeah.
Okay. Is not what's often denoted by a slash?
No, it's not the supergroup. It's
okay.
I should have, my mistake. I should have put there a comma. But it's just SO2, 3. And this is for all of us well known to be the conformal algebra in 2+1 dimensions. And so in this case, just by kind of repeating this very simple kind of example, we saw that the non-relativistic symmetries conspire to generate a full 2+1 conformal symmetry. You might ask, well, why is this? Where is the symmetry coming from? And that's actually because this Lagrangian is a free scalar field in light cone coordinates. So if you go to coordinates which are x plus y and x minus y, then this term just becomes Laplacian squared, and you would see that it has a full, it's just a free scalar field in 2+1 dimensions and has the full 2+1 dimensional conformal symmetry. But by looking at it, you might not realize that that's the theory you're looking at. And it is in a different coordinate system, and So that's maybe how you might want to make sense of the spectrum of this theory. Going back to questions from before, well, how would I make sense of this theory? One way to do it is to realize that you're working in the wrong coordinate system, and that really.
I'm sorry, I still don't see. So if you change to other variables, say z and w, which are x plus and minus y, what are you going to get there? Are you going to get dz square minus dw square?
Yes.
So then all the question that Michael asked before becomes even more pronounced because one of them has the wrong sign.
Right. And so really one of them needs to be the time variable.
I see. So are you saying that here we should think of the Euclidean time as space and x and y as being space plus or minus time?
Based on this analysis, that tells you that that's the right way to think about this
But
theory.
this is a totally different Hamiltonian, the one you started with.
It is a
same time.
It is a different Hamiltonian.
I see. Thank you.
Yeah. So I think more than maybe trying to make sense of this in the original coordinates, this is just maybe some simple example where we know what the answer should be, and somehow these subdimensional conformal symmetries worked out to give maybe what you would have hoped the relativistic symmetry to be, and it's just some sort of toy example of what might occur in such theories. And so if we look at all of them, a similar thing happens in this 1-2 theory, where again we have this weird sign in the Schrodinger algebra. This is kind of the same idea where if you move to light cone coordinates here, you get this weird sign. But here the Hamiltonian in this original coordinates is fine. Like I argued, if you think of phi as a fermion, then this theory is completely has a great spectrum. Everything is fine, but somehow still the subdimensional, in this case, it just has some sort of holomorphic conformal symmetries, created a Schrodinger symmetry with some weird signature. Okay. So, so maybe a few conclusions about this, about these toy models, is that as we've seen, they can have, a lot of these models can have or have these subsystem conformal symmetries, and they and these symmetries are really novel and have this intricate conformal structure, and they form, in some cases, some nicer closed algebras that maybe we can understand, and in other cases, they don't form any sensible algebra that we can understand, and they just kind of generate more and more operators, and so maybe they constrain the theory even more. And this already exists in free theories in 2+1 dimensions. We can always go to more dimensions and look at other theories with similar structures. And so maybe I'll talk a little bit about what else we can do. So one thing we can always do, like I said, is go to higher dimensions. For example, we can take more spatial derivatives, up to n, and do the same exact thing. And again, this would have some sort of subdimensional conformal structure, again acting on any time and any plane coordinate. We can also maybe look at interacting theories, which is something I'm currently looking at. We're adding some sort of interaction to the Lagrangian, but maybe more interesting is to look at interacting, try and find interacting CFTs by maybe finding or driving some sort of rule-sufficient-like transition, which goes back to questions that were asked earlier, which is, well, are there any maybe more interesting CFTs we can, fractonic field theories we can find? Well, one option is to try and drive a will-sufficient-like transition. And so how would you do this? Well, you would want to look at the global symmetry and look at some sort of phase transition between the spontaneously broken global symmetry and the unbroken symmetry. But to break a global subsystem symmetry, at least a continuous global subsystem symmetry, you would need a codimension bigger than 2. And this is due to the generalized Mermin-Wagner theorem. And regular Mermin-Wagner-Coleman, you need at least 3 dimensions to break a continuous global symmetry. So if you have a symmetry that only acts on a subspace, you need the codimension to be bigger than 2 instead of the dimension to be bigger than 2. So for example, if you take a theory that has the same global structure that we had before, this symmetry just acts on lines. And so in 2 + 1 dimensions, that's not enough because the codimension is exactly 2, right? If we have symmetry that acts on lines, the codimension is 2, so it can't be spontaneously broken. But going 1 dimension higher, for example, maybe looking at such a theory, or the 3 + 1 dimensional analog of such theories, you might have a spontaneously broken phase where the symmetry is spontaneously broken, and then you can try and maybe tune second order phase transition between the broken and unbroken phase. And that's currently more work in progress. And so that's maybe, that's all I have to talk about. Thank you for listening. Stay tuned for more. And this is a very exciting time to work on these questions. And there's still a lot of stuff we don't know about these types of theories.
Can I ask something?
Yeah.
Yeah, you said you want to study something like a Wilson-Fisher fixed point, then you turn on interaction. Is it obvious that the interaction preserves a subsystem symmetry? Only look at the interaction which actually preserves subsystem symmetry, because actually if it does not, it will generate what?
Yeah, I mean, you'd want it to preserve the subsystem symmetry, right? Otherwise, you don't know, you don't have any control about the fixed point. You definitely don't know that the fixed point will have anything to do with the subsystem symmetry.
And what kind of, for example, 4-particle term or 5-4 term, imagine which actually preserve the subsystem symmetry?
So there are various options to do it. One way is to just maybe couple such a theory. So if we go back, one option might be to couple such a theory to matter terms, okay, and then have the matter terms drive this Wilson-Fisher-like transition. Because here you can't add a phi to the 4th term, right? It doesn't preserve this interaction. Another option is to go to maybe what?
Sorry. Can you explain me what kind of matter term do you mean? That phi here is the scalar field, it's not a gauge field.
Fields, for example, you might want to add a field, either a field that doesn't transform under the symmetry, but you can just couple it to it in a way that preserves this dipole symmetry. Like one option is what I talked about before, some sort of coupling with dx dy phi. But maybe a more interesting way to do it would be to have a field that for example, transformed by a phase under the symmetry. Right?
That term you wrote down, like side by side, partial x, partial phi phi. Partial y phi. That term looks pretty irrelevant. Is that right? Or
yeah, well, in 2 + 1 dimensions, it's marginal.
But there's a very
if phi is non-relativistic scale.
Okay.
There's a very simple way to do that. Consider a field big phi, which is roughly e to the I little phi that you wrote there, on which it acts linearly, and then write a standard theory with some derivatives that act on it.
Mm-hmm.
So using the field phi that he used, it's not easy to do it because the symmetry acts non-linearly. But if you have a complex field, big phi, which is roughly e to the I little phi, and the subsystem symmetry acts by e to the I alpha f of x plus f of y, then it's relatively easy to write interactions that preserve the subsystem symmetry. I think Mike Hermele and collaborators considered transitions involving a coupling roughly can be translated to the statement that there are phase transitions where such a phi condenses or does not condense, and the two sides of the transitions, the subsystem symmetry appears to be spontaneously broken or not. So
yeah, sort of. I mean, I think you're probably thinking of the paper with Han Ma and Xie Chen. I mean, we were really just thinking about the phases though, and not the properties of the transition itself. So there are some, assuming there is a continuous transition for some of those situations we studied, I think its properties would be interesting, but we were not able to, we weren't trying to say anything about it.
But in any way, to answer Chenka's question, such a Lagrangian is easy to write down, and it has interactions and it has the subsystem.
Yeah, I agree. It's easier with a complex valued phi rather than just a compact, like a real compact scalar phi.
Mm-hmm.
Amir, I had a question actually about the last part. So, so why focus on continuous subsystem symmetries? I mean, why not? Is there some problem with trying to look at transitions where there's a discrete subsystem symmetry that gets spontaneously broken?
There's no problem with that. I mean, that's also interesting. And you can try and do something very similar where you have a discrete subsystem symmetry. And then you can do it in 2 + 1 dimensions. We were just trying to build up on these types of continuous, these theories that have a U1 transition. And also it might be easier to figure out, to understand if the symmetry is broken or not broken, just because you have Goldstone modes or you don't have Goldstone modes. While if you're looking at a discrete symmetry, it might be slightly harder to understand if the symmetry is broken or not. But that's definitely an option, and that would also be very interesting to do.
Okay, good, thanks.
I have a quick question. For the XY plaquette model, you said that the algebra is pretty big and it's hard to find generators for it. Does the fact that the subdimensional conformal symmetry is sitting inside a Virasoro algebra help or make the problem worse?
It doesn't help, or at least it doesn't seem to help. You can write down all the generators of the Virasoro algebra, and we did that. And then we started trying to commute them all, and they still don't close in on themselves. We also tried just starting from the global conformal algebra, and that also didn't seem to help or hinder. They both seem to create this require infinitely many additional terms.
Got it, thanks.
Sorry, on this slide, I think I'm missing something basic. So you say you need your symmetry to act on lines. The bottom Lagrangian, aren't the symmetries on planes?
So you shift phi by a function
Of x, for example.
of x plus a function of y plus a function of z.
Right. So you can make the function of x have support on only one value of x, but isn't that a plan?
Shuang, I think you're just misreading his slide. He tells you that the theory he studied so far, he has it acting on lines. Therefore, he needs to now go to a new theory like the one he wrote down at the bottom where it acts on planes.
Yeah.
The one at the bottom is the good one. The one he discussed before, it doesn't work.
Okay, but you, at the end of the day, you want the symmetries to be supported on lines or on planes, or what was the?
So you want the codimension. So like a general global symmetry, it acts on all of space. Okay.
Right.
And
codimension
then,
one in space time, right? In your term.
Amir, I think codimension was probably the wrong word there, right? You need the symmetry to act on 2 dimensions or more, right? So
okay, maybe this codimension is
right.
the wrong word.
Codimension, right? Yeah,
it's not the codimension.
Right. Okay.
Yeah.
Okay, that's good. I was a little confused by codimension there too.
Yeah. Okay.
Right. Thank you. Yeah.
Sorry about that. That's a little inaccurate. Any other questions?
So if there aren't more questions right at the moment, I think this is a good time to thank Amir for a really nice talk. So thank you. And I'm going to stop the recording now.